think absolutely perfect would be. Okay, so our types of forces, ionic electrostatic. Anybody think they've got it absolutely perfect? That's a bit mean. Let's not do that. Anybody think they've got information that should be tied to ionic or electrostatic forces? I saw you first, Ness, and then we'll go to Tim.
Sodium chloride.
Okay, so as an example, sodium chloride would get us an example of an ionic or electrostatic intermolecular attraction.
It's a metal to non-metal, and the electronegativity should be.
Okay. Whoa, 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 whoa. Barely writing metal. I'm going to come back to that. Let's see if somebody else has an option there.
It is the strongest of the four.
For those of you who thought hydrogen bonding was the strongest of the four forces, it's probably because you took a biology class. Just for the record. Okay. Anybody else have anything else?
Greatest electronegativity.
Okay. It generates the largest difference in electronegativity, which is, I think, where you were going.
1.7.
Okay. What just happened? Okay. So difference in electronegativity. How do we signify difference? Because we're lazy and don't want to write difference. Yeah. Our delta symbol. Okay. Electronegativity has way too many letters in it. The symbol generally accepted for electronegativity is, it's not really X. I'm not good with the Greek letters, but I think it's chi. Yeah, it's an X with a hook. Okay. So the difference in electronegativity needs to be greater than, needs to be greater than 1.7. So if we bond a metal to a nonmetal, we typically see electronegativities greater than 1.7. Why? Where's your most electronegative element?
Right
The
side of the
upper right-hand corner, which happens to be? Keep going. Fluorine is a nonmetal. Where are our metals? The lower left-hand corner, which happens to be the least electronegative. So when we bond metals to nonmetals, we are typically seeing a drastic difference in electronegativity. So as a general rule, we could use metal to nonmetal to help us classify ionic compounds. Officially, it comes down to the difference in electronegativity. Okay? How many people have any of the electronegativities memorized? Ooh, do we want to memorize greater than 1.7? No, because at best you know one. That's not useful to get a difference. Okay? So as a general idea, metal to nonmetal is the best thing to memorize for your ionic electrostatic. There are exceptions to that, but for the most part that works. Okay? So important information, we'll try and underline in black. Metal to nonmetal and strongest. The first suggestion that came out was actually a really good one, coming up with an example. If you have an example, now you can start to make classifications based off of that. So the example that Ness suggested was sodium chloride. Well, what is sodium? A metal. What is chloride? Nonmetal. You now have something that you can use as a definition. Does that make sense? Okay. So examples are helpful. How many people had all of that? Was all of that in the video?
And then you erased a bunch of it.
Yeah, I did. Okay. So all of that content was there. You saw it all. Why did you not memorize it all?
I didn't write it down.
Okay. You may not have written it down. You may not have taken notes. Okay. You may not have studied it as intensely to make sure you knew all of that content. Okay. A lot of what we talk about in this class needs practice. You have to go back and refer to those notes. Okay. Unfortunately, and you can blame this on me, really the only times that I test on your ability to go back and refer to those notes is for the exams. So you hit a high stress value point to test on that. You don't get a bunch of little quizzes in between to be like, what are you doing? Why did you not do that? Right? So when it comes to the final, start doing that review back. Start trying to find that. Okay? In general, you guys have been outperforming every other semester. You're already doing a pretty decent job at it. Keep doing it. Okay? I'm going to skip hydrogen bonding. Why might I skip hydrogen bonding?
Because it falls under dipole-dipole.
Hydrogen bonding is a special case of dipole-dipole. So what I would argue is there's 3 intermolecular forces with a subcategory. So there's like 3.5 intermolecular forces. And I actually forgot, we're missing a piece of information for the ionic electrostatic. Okay. Officially, sodium chloride, metal to nonmetal. Sorry, I just noticed that. Aren't actually correct. Right? They're borderline, and that's only because of where ionic is as a force. Okay? The ionic or electrostatic force comes from different molecules interacting with each other. If I just look at sodium chloride, am I looking at different molecules? No. So I would be looking at the intramolecular force for sodium chloride. That intramolecular force is now such a stronger force that I no longer call it a force. I call it a bond. Why might we have left that off here? What is the name of that bond in the ionic or electrostatic force? Ionic. Okay. Scientists not the most creative. We have 2 separate categories, bonds and forces. Okay. The bond is different than the force, but an ionic bond will generate an ionic force. Okay? So another piece of information is that we could write ionic bonds as our source. Okay? This is where, oh geez, I saw somebody draw it better than what I just did. Okay? This thing, where they listed out each of the forces, and then what was it tied to?
Yeah.
It was tied to the bonds, was the word you were searching for. Where we have forces on one side and bonds on the other. Okay? Wasn't done very well in the video, but ultimately what we're looking at here is any kind of attraction between any 2 atoms. Any 2 atoms. Okay? If those 2 atoms are strongly attracted to each other, I'll say they have a bond. If it is a slightly weaker attraction, I will say there's a force. Okay? So I'm differentiating between bonds and forces. Kind of like I'm differentiating between physical and chemical changes. Okay? Same concept. And in physical and chemical changes, it's a spectrum. At one end of the spectrum, we would call it purely physical. At the other end, we would call it purely chemical. The same thing is happening with this intermolecular or this atomic attraction. If the atomic attraction is very, very strong, we have a bond. If it's weak, we have a force. So why aren't we looking at it, I see your hand, I'll get to you, as just a linear relationship? Okay, where we have bonds over here and forces over here. Because if I do that, we'll use the one information we've got so far, we have ionic forces and we have ionic forces. They're right next to each other. This is why it can be confusing to deal with them. Because when we cross one part of that line, we're looking at a bond. If we go to the other side, it becomes a force. Kind of like dissolving salt in water. Was that chemical or physical? Oh, that's fun. We just had 2 answers shouted out. Okay? Depending on what information you're using, you may classify it slightly differently. The ionic bond versus the ionic force is similar in concept. It's right on that threshold. It's an arbitrary line. Okay? That arbitrary line is sometimes hard to differentiate. So why, again, do we try and put it as the circle and not as a straight line? Well, the ionic ties to ionic. What's the next force after ionic? I'll accept 2 answers, the only one I really want. Ionic forces, we said. Dipole-dipole. So I could look at a dipole-dipole force. Okay? as we start to now address, well, what makes a dipole-dipole force? What information could we add to that? What information do you have for dipole-dipole? So one suggestion was everything else.
It's not metal, non-metal.
Okay, that's going to be a hard one to nail down, but we'll work with it. Non-metal to non-metal.
Polar.
I keep dropping that stupid N. Okay, it comes from polar covalent bonds, which is the one I was fishing for here. So if we go back and look at this, we have a dipole-dipole force. A dipole-dipole force comes from a molecule that has polar covalent bonds, which happen to be stronger than ionic bonds. So it moves to the left. Do you see a relationship between polar covalent and dipole-dipole in this linear fashion? No, it becomes harder to see. Hence, cyclizing it, because when we cyclize, we can then go back and draw saying we have polar covalent. Whoops, of course I wrote it on the wrong side. We have our dipole force going to our polar covalent force. And we can do that crossing and see how those intermolecular forces are tied to the bonds. Does that make sense? So that's the point of making it cyclic. Ultimately, it is a linear relationship. We're arbitrarily dropping lines for interpretations. Kind of make sense? Okay. Does anybody believe that's nonsense? We aren't dropping arbitrary lines. No one's combative today. Okay. The example I would use would be a rainbow. What colors are in the rainbow? All of them. And yet, what are we told are the colors in the rainbow? Roy G. Biv. What happened to all the other colors? Okay. We get, I don't know my colors well enough. We get fire engine red versus brick red show up in the rainbow. Why isn't it not including fire engine red when I say Roy G. Biv? That's too hard to include all those colors. We're coming up with arbitrary cutoffs to simplify our analysis. What's happening with our bonds and forces? Arbitrary cutoffs to simplify our analysis. Okay. Where it becomes tricky is when we land on a place where that cutoff can reflect on both sides. What is the difference between an ionic bond or an ionic force and a dipole-dipole force? That can become hard to tell if I have something falling immediately in that line. Which means typically when we look at differentiating these, we look at the big examples, just like we did with physical and chemical changes. You're expected to address the big ones, not the gray areas. Make sense? Okay, I think I saw a hand somewhere before I start erasing stuff. Gonna know? Okay, you're gonna raise your hand right after I erase, aren't you? Okay, good. So I'm gonna, can I erase everything? Well, everything, just the pictures that are in the way. Okay, so what else do you remember about the dipole-dipole? We have everything else. We have non-metal to non-metal, polar covalent. Okay, weaker. What do you mean weaker?
Weaker than ionic.
Okay, it's weaker than ionic, and then I heard the other important one, stronger than van der Waals or London dispersion, and because I'm lazy, LDF, London dispersion force. Okay, what else could we identify about it? Because I would argue there's at least two more pieces of information that we should include. The difference in electronegativity is between 0.5 and 1.7. So it's less than 1.7 because it's not an ionic bond, but it'll connect eventually. But it's greater than 0.5, which might give us some information for the next one. Whoops. What's the issue with memorizing the difference in electronegativities?
Then you have to know how to measure them.
Then I would have to know the electronegativities. And if I don't know the electronegativities, that definition doesn't help me. Okay? It is useful, but only in as much as I know the electronegativities. Okay? The next part on this that you need to watch out for Are those numbers absolutes? No. Depending on who you talk to, they change slightly. I've seen the 1.7, I think, drop as low as 1.5. Okay? So depending on the textbook reference, they may do something slightly different. So just be aware of that. And I'm actually going to back off of oxygen to hydrogen. Okay? So what Tim is suggesting is that we should also provide an example. Just like Ness did with the ionic with sodium chloride, I want an example for a dipole-dipole. Which one's going to get me a dipole-dipole? Okay. OH was a suggestion, and I said, I don't like that one. And we'll see why I don't like that one in a little bit. What's another one? Another example. Okay, carbon and oxygen. That one's now one that I would accept. Okay, so non-metal to non-metal, polar covalent bond. How do I know that's a polar covalent bond? Okay, let's stick with the non-metal definition and hold that for a second. What do we know about London dispersion?
Also, non-metal.
Non-metal to non-metal. Why is our definition for dipole-dipole now questionable? They're both non-metal. Fudge nuggets. I did it right once. For whatever reason, the second time, I can't put the N in. Okay? So both of them are non-metals to non-metals, which means that definition, not useful, not worth memorizing. Okay? What other things could we remember about London dispersion?
Same atoms, atom to atom.
Okay, atom to atom, I know where you're going with that. Okay, so same atom to same atom. What is that getting to?
Carbon to hydrogen.
That is getting to the fact that that has a low difference in electronegativity.
Right. Those two pieces of information taken together are getting at two pieces of things. Number one, that our difference in electronegativity is tiny. How tiny? It's less than 0.5. What else does it get to?
Non-polar.
It is a non-polar covalent bond. Okay. What other information could we write down for our London dispersion? What's that? Okay, this one's our weakest. We actually already came up with examples. Our carbon to hydrogen and same atom to same atom. We got the non-metal to non-metal. We've got the weakest. We got our difference. We have examples. And we've got the type of bond, non-polar covalent bond. So cool, we've got all that information. When we go back up to this one, I entirely forgot what I was not going to write about the dipole-dipole. Was anybody in my head?
Why is carbon and oxygen dipole? That was the last.
Why is that a better example than HO is what you're about to go over?
Why is carbon to oxygen a good one? Let's start with that. It's our difference in electronegativity. What can you tell me about oxygen? It's the second most electronegative element. I bond oxygen to pretty much anything, and what do I have? I have a polar covalent bond, which is going to generate dipole-dipole forces. Okay? Kind of make sense? When we go to the hydrogen bonding, we had another example thrown in there. We had the OH as an example. What stuff could we identify for it? Hydrogen bonds? I don't know what that means.
So
It's hydrogen bonding. What else would we write there?
Hydrogen and carbon is your only one in London dispersion, and then every other hydrogen bond would be hydrogen bonding.
No.
No.
Hydrogen to chlorine is not hydrogen bonding. Try again. I need a hydrogen bonded to what? Oxygen, nitrogen, fluorine, not carbon. Did you say carbon? Yeah, not carbon. Carbon does not generate hydrogen bonding. Okay? Some people like to call it phone. Hydrogen bonding is all sorts of fun. I don't know. I didn't come up with it.
So it's just the three highest electronegative, right?
Personally, I've had enough. Sorry. What's our difference in electronegativity? Oh, that's going to be kind of hard. Right? What is it? It's high. It's really high. Fluorine, oxygen, nitrogen happen to be the highest. First most electronegative, second most electronegative, third most electronegative. So when I take any of those top three elements and I bond them to hydrogen, which happens to have what kind of an electronegativity? Not just lower, it's so low, where is hydrogen typically classified?
By itself.
On the non-metal side of the periodic table. So hydrogen's electronegativity is so low that it is roughly a metal. So we are looking at a bond that is effectively an ionic bond because of that difference in electronegativity. Right? Because it is effectively an ionic bond, why don't we call it an ionic bond? It's not a metal to a non-metal. What is it? Oxygen and hydrogen are both non-metals. So why don't I classify it as a dipole-dipole?
It is, because it doesn't meet the electronegativity.
It does meet the electronegativity difference. That interaction is so stupidly strong
That's why it gets its own special.
that it gets its own special subcategory. Right? The hydrogen bonding interaction is a dipole-dipole. It's just a special case of one. It is such a strong dipole-dipole that it is important enough for me to identify and say, I need to look at this. Why might it be important enough? What is our solvent for 70% of the reactions we do? Water, which has hydrogen bonding. Why do we have life? Water. Okay, virtually everything that we know about our existence is due to water being there. One of the things that water has, hydrogen bonding. It is that hydrogen bonding attraction that is so important that we call attention to it and differentiate it as its own thing. Okay? Yes?
The London dispersion, if you bond to the same atom, and then give an example of carbon and hydrogen,
Mm-hmm.
how are those the same?
Those are two different examples.
Those are two different examples that fit within the London dispersion. Right? So our London dispersion officially falls the difference in electronegativity. That sucks as a definition to have to memorize. Okay? So what we can do instead is memorize this to help us out. And really what that thing is helping us out with is really telling us that we have what type of bond? A nonpolar covalent bond. Now that I know I have a nonpolar covalent bond, I know I have London dispersion forces. Since I know they're London dispersion, I know that they are the weakest. Okay? So, back to the everything else comment. There's a lot of crap that falls in the dipole-dipole area. Okay? There is so much stuff there that we don't want to bother to try and have to memorize electronegativities. So instead, what do? We memorize the others. When it doesn't match those definitions, process of elimination, it's dipole-dipole. That allows me to relatively quickly assign the strength of the force possible for that compound. Right? In each of these cases, really what we've identified is looking at a molecule and then said, how does that molecule interact with its outside environment? Right? It's that attraction that we're concerned about. Make sense? Questions about those definitions? Okay. Now that we've worked through it a couple times, you know to review and make sure you got those on lock. Why? Because ultimately what you're going to have to do, there's that pretty picture, by the way. What you're going to have to do is apply those forces. I don't care that you look at a compound and say, oh, that has hydrogen bonding. I care that you look at a compound and say, that has hydrogen bonding, that one has London dispersion forces. Because of that, that hydrogen bonding compound is going to have different properties. How different are they? Well, it depends what property I'm looking at. Okay? So what you have to do with this is apply this knowledge out. Okay? To do that, you have to be able to look at the compound, identify the bonds. Once you know the bond, you then know the force. Once you know the force, you can then establish a strength. You can apply that strength to one of your potential observables. Right? For the sake of this class, we're really only looking up at phase transitions, which is a fancy way of saying vapor pressure also. The rest of these, well, actually solubility, we also look at. The rest of these get kind of talked about in the textbook, but don't really get evaluated or tested on. We're really concerned about solubility, vapor pressure, and phase transitions. Reactivity is a neat one. Guess what OChem does? Just that. All of OChem is taking those bonds and forces and coming up with how those things should react. This is OChem on one slide. Okay? Easy, right? Okay. Don't worry, you only spend a year doing it. Of course it's easy. Okay? So, melting point and boiling point. What is a melting point? A phase transition going from solid to a liquid. Okay? So which compound would have the higher melting point? So as I go from solid to liquid, if I say higher melting point, what does that mean?
Meaning it takes a higher temperature to take phase transition.
It's the point at which something melts, and if we're saying the higher melting point, it's the higher temperature. Okay? Which means what do I have to do? Put in a lot of force or a little force to cause them to break apart? A lot of force. Which means what are those individual molecules doing to each other? Are they holding on to each other tightly or weakly? Tightly. So a high temperature means a strong force. How do I get a strong force? We could go back to the bonds. Okay? And this is where it gets a little bit weird. What kind of bonds would I be looking at to get a strong force? An ionic bond, which happens to be the weakest bond, which tends to trip people up since it appears to be backwards. Okay? The strongest force comes from the weakest bond. Okay, well, that doesn't make any sense. Let's run through it real quick. Let's look at the opposite. Let's look at a strong bond. If it is a strong bond, does it want to interact with anything? Okay. Couples that have been married and really have a strong attraction, would you expect them to cheat? No, why not? They have a strong bond. So their attraction with another species is null or minimal in theory. Okay? What if you have a very weak bond? You have a marriage that is very weak. They don't really like each other. Would you expect them to interact out with other couples? Yeah, in fact, they would probably have a stronger attraction outwards. Why? They have a weak interaction to begin with. Okay? It is a challenging concept to deal with, but that's ultimately what's happening. So what I'm looking for, higher temper, stronger force, which means weaker bond. What's my weakest bond? LDF is not a bond. That's a force. Okay. Our weakest bond is the dipole-dipole is also a force. A nonpolar covalent bond would be the strongest bond. When we look at this, increasing polarity is really just going straight up. Remember, this was a straight line that we broke apart. Okay? The covalent bond, or nonpolar covalent bond, is the strongest possible interaction between any two compounds. London dispersion is the weakest force. So what we're doing is pulling this out black to black. Okay? And it continues all the way through. As the covalent bond becomes weaker, what happens? It becomes a polar covalent bond, which then becomes an ionic bond. Once we have an ionic bond, eventually what happens? It becomes an ionic force. As that ionic force becomes weaker, what do we become? Hydrogen bonding to dipole-dipole to London dispersion. Okay? London dispersion interactions come from nonpolar covalent compounds. Why would they generate the weakest force? A nonpolar covalent compound has the strongest bond. That is the couple that is on lock, that is never going to interact with the outside world. Okay? Because they don't interact, they generate weaker forces with the outside environment. Okay? That's kind of the process. We need to look at both the linear aspect and the circle. Kind of makes sense? And of course I deleted all of that work that I wrote there. So in this case, if I'm looking for the higher melting point, I'm looking for the strongest or the weakest bond, which would be ionic, which would generate the strongest bond or the strongest force. I can't see forces, I can only see bonds. Anybody see an ionic bond anywhere in this list?
Sodium.
Number 4, what did you look for to find that ionic bond? A metal. Because that's when we have an ionic bond. So in this last example is the easiest one to look at. We have an ionic bond versus hydrogen bonding is a phenomenal answer for a force. I didn't ask for a force, I asked for a bond. What is the bond between oxygen and hydrogen? A polar covalent bond. Because it's not same to same, it's not carbon to hydrogen. So polar covalent bond is that weaker or stronger than ionic. Stronger bond, which means the ionic bond is going to generate the stronger ionic force, which means that's going to have the higher melting point. They don't separate easier, it's harder to separate. Okay? You get lots of kind of back and forths. You have to be careful with those back and forths when you go through and deal with melting points and boiling points. We'll pick up there Thursday.